So we're going to do online Excel Lab 4. It's a probability lab. Now it looks like there's 2 problems. But the second one, there's only like 5 answer boxes. So that one should go pretty quick. The first one is just kind of like probability rules. So I don't think this video should take very long tonight. There's only 2 questions too, so. All right, so we're gonna copy the data. I'll copy the table into Excel. I'm only going to copy the first 3 rows of the table, and I'll show you why in a second. Oops. I'll show you why I'm only going to copy the first 3 rows of this table. And again, when you paste something into Excel, like a table, you want to strip away the HTML formatting that might be there. So always paste it as match destination formatting. I'm going to center it. Well, actually, I'm going to left justify it. And then I'm going to grab the first 2 rows. I'm going to highlight the first 2 rows like this. One way to highlight the first 2 rows is to click once on cell A3, and then hold down the shift button. Go to the right with the right key, and then go down 1 with the down arrow, right, on the keyboard. And then I'm going to grab the bottom, a green square on the bottom right-hand side of those highlighted cells. I'm going to change my cursor into a black cursor. I'm going to drag it down until I get to 16. Okay. Everybody see that? That's an easy way to make a series of numbers, right? That increase by 1. All right. Now we want to draw a spinner that has 16 numbers on it. So I'm not going to draw it. I'm going to look for one on the internet. Wow, this is cool. I Googled spinner with 16 numbers, and I get this Google app. That's pretty cool, right? You guys see that? I Googled spinner with 16 numbers, and Google gave me this spinner, and I just set it at 16, right? And you can spin this wheel, right? Any fans of the Price is Right? Any fans of How I Met Your Mother? Barney in How I Met Your Mother goes on The Price is Right, and he wins every prize. And he also wins at the big wheel. He gets everything, 100%, wins everything, right? And then he donates the gifts to his friends. So let's ask this question. Let's go back to the problem. You know what I had to do? I had to come up with the share this. Copy. This is cool. I had to share this on the problem itself. Yeah, that's actually pretty cool because I wasn't even thinking that you can do that. That thing was even available.
After you're done, can you show me how you did the count on the X's again?
Yeah. I'm going to put the spinner app in the problem itself. It'll be really cool. I'm going to save it. I'm going to go ahead and enter garbage. Don't follow what I'm doing here. I'm entering it. I get my spinner here, right? There we go. That's cool. So you can click that and you get this. You don't have to look for it. Cool. And I'll call it Google. I'll give Google credit for it since it's a Google spinner. I'll call it a Google spinner. There we go. We'll give Google the credit. Okay, what you need? Who is that? Who needed me to do something?
It was me. I'm sorry. I just needed you to show me how you did the count in the A column again. I don't know if I'm doing it right.
Oh yeah. Well, I mean, what you could do instead of what I showed you, you just do this. Oh, by the way, you want to do these problems? Use the same Excel worksheet, but or use the same Excel file for the entire semester. That way you have a nice dossier when the semester's over with. And then in future courses, you can refer to this one Excel file. You can just put these worksheets. You can keep adding them to your file here. So you can add worksheets down here. And then if you have all of your models in this class built out in this one Excel file, you'll have a nice dossier or portfolio when you're done, right? So what you could do is you could just type, it might be easier just to type X, and then P stands for probability of X. This is the probability of X, and that's X, right? So then on here you could type 1 and then a 2. And then if your last number here is 16, these two numbers should match, and yours might be different than mine, right? How many people have 16 right there? Does anybody have 16 right here? Or do you have different numbers?
No, I have two.
Does everybody have 16?
They're
I
different.
have 12.
Okay,
I got
cool.
10.
All right. So what you want to do is you want to, whatever this says here, it'll be the same number there. And then you want to highlight the two numbers and go down until you get to the end right there. 16, see that? 16. So I made enough numbers here so that this last number matches that number. And this colon here, the two dots, that's just my way of saying yada, 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 right? There's a bunch of stuff in between. So this table really should look like this, right? The table in the MyOpen Math problem, in my MyOpen Math problem should look like this, right? Everybody see that? Okay, and then when you build your spinner, right? When you build your spinner, just choose the right number of numbers, right? Okay, and then you can spin the wheel, right? Okay, now in my problem, what is the probability of spinning a 1? In my problem, what's the probability of spinning a 1?
1 out of.
Yeah, 1 out of 16, right? Whoops. Yeah. What's the probability of spinning a 2 in my problem? Still 1 out of 16, right? Why is that? Well, the space for 1 is the same area as the space for 2. Each of these slices of pizza have the same area, right? And because they have the same area, spinning a 16 or spinning a 2 is 1 in 16, right? Because this area is 1/16 of the entire circle, right? This area is 1/16 of this entire area. Now, if 9, 10, and 11, if the area of 9, 10, 11, or sorry, if 14, 15, and 16 were one slice, right? If 14, 15, and 16 were one slice, and this was 14, then the probability of rolling a 14 or spinning a 14 would be 3 divided by 16, right? Y'all see that? If this slice of pizza here, if this slice of pizza here, the 13, the 14, the 15, and the 16 were one slice, and this were all 13, then the probability would be 1, 2, 3, 4 divided by 16. Why? Because this is 1/4 of the pizza, right? But each one of these areas is the same, right? These areas are exactly alike. They are of equal area, right? So the probability is 1 in 16 for all of these, for me, right? So once I have that one, I have all 16 of them, right? And a probability distribution, it's a probability distribution if each probability is between 0 and 1, and the sum is 1. The sum of my distribution, let's type equal sum down here. Sum of my distribution is 1. You see that? So if you have 12, you'll want to stop, you want to delete those right there, right? You won't have these down here. And then this will be 1 divided by 12 instead, right? If you have 10, if you're putting 10, if it says 10 numbers on it, and that's 10, then each one of these would be 1 divided by 10, right? Instead of 1 divided by 16. Any questions on that? So I'm going to change this to 0.0625. I'm going to copy that. I'm going to hit tab, paste it, tab, and then I'll hit enter to see if I got it right. I got it right. Yeah. Now the probability of the spinner landing on an even number, that probability is what? Well, how many even numbers do I got?
You have 8 in your case.
Yeah, I have 8 in my case, right? I have 1, 2, 3, 4, 5, 6, 7, 8, right? 8 light green areas. Now, if your number is 15, right? If your number is 15, if you're given 15 on a spinner, your probability is not going to be 0.5. My probability is 0.5, right? Because the probability of being even, I'm going to add up these values here, right? Everybody see that? That's the probability of 2. That's the probability of 4. That's the probability of 6. That's the probability of spinning 8, 10, 12, 14, and 16, right? So this is the probability of even. Another way to think about that is probability of a 2, or spinning a 4, or spinning a 6, or spinning an 8, or spinning a 10, or spinning a 12, or spinning a 14, or spinning a 16. When the word is or, you add probabilities, right? when it's or, you add the probabilities, right? And you can only add probabilities if the events are mutually exclusive. What does that mean? Can I spin on one try? Can I spin and get a 2 and a 4 at the same time? Can I spin a 2? Can my spinner, when I spin it once, right? When I spin it once, can it land on 2 and 4 at the same time? No, right? So 2 and 4 are mutually exclusive. 2 and 3 are mutually exclusive. 1 and 16 are mutually exclusive, right? So all these events, these 16 events on my spinner, are mutually exclusive, which means if I want the probability of the union of the even numbers, I can just simply add those probabilities up, right? Because these are mutually exclusive events. Oh man, that's awesome. Thank you. Oh, you got me too? Oh, I don't need that, but that's all right. Cool. You didn't get 12 different kinds?
Oh, really? Oh, yeah.
Thank you. No, I was expecting 15 different kinds. Any questions on that? So each one of these numbers, any group of these numbers, they're mutually exclusive events. So you can just add those probabilities up, right? Another way to think of it is I got 8 even numbers, and I got 16 numbers. 8 divided by 16 is 0.5, right? Now, if this is even, if it was 15 instead of 16, it was 15 instead of 16, what would you do? What the heck? If I only had 15 there, right? If I only had 15 there, this would be 1 divided by 15, right? So this would be 1 divided by 15 instead of 1 divided by 16. Then I'd just add these up, right? You see that? Yeah, good. All right. So this is 0.50. Hopefully this isn't too difficult. It's probably getting less than a 6. Okay, so my number here is 6. Your number is going to be different, right? So I'm going to do is I'm going to come over here. Is 1 less than 6? Yes. Is 2 less than 6? Yes. Is 3 less than 6? Is 4 less than 6? Is 5 less than 6? Yeah. All those numbers are less than 6, right? Is 6 less than 6? No. 6 equals 6, right? So in this case, I want to add these 5 probabilities. So when you read the probability of getting less than 6, another way to say that is the probability of getting a 1 or a 2 or a 3 or a 4 or a 5, right? So in my case, this probability is 0.3125. When the word is or, the events are mutually exclusive, you just simply add the probabilities. The union is a very inclusive club. The intersection is a very exclusive club, right? We're talking about unions here, right? Okay, what about the probability of getting a number greater than 4? I got to get rid of these here, right? 5 is greater than 4. All these numbers are greater than 4, right? So I'm going to just drag this down. Yep. Everybody see that? So you can think of this as the probability of 5 or 6 or 7 or 8 or 9 or 10 or 11 all the way down to 16. Again, when the word is or and the events are mutually exclusive, you can just simply add those probabilities up, right? So this is 0.75. What about probability getting a 7 or a 4? I'm going to delete everything but, oh, yeah, I'm going to delete everything but 7 and 4 right here. I'm going to copy that and put it right here. They're probably getting a 7 or a 4. Again, the word is or. 7 and 4, you can't get 7 and 4 at the same spin. So 7 and 4 are mutually exclusive. So I just got to add those two things up and I get 0.1250. Is everybody able to get correct answers on that? Easy stuff, right? Any questions on that?
Yeah, I'm trying to catch up.
What's that?
Yeah, I'm trying to catch up. Yeah, I said, yeah, I got it. I'm just trying to catch up.
Okay, so you're good? Do you need a few minutes before we move on?
Yeah, just a few minutes. Yeah.
Okay.
Yeah, I
Everybody
need
else
a few
all
minutes
right with
too.
that?
Yeah, I need a few minutes too.
Okay. If you want to share your screen with me, I can help you out too if you want.
Do you want us around?
What's that?
Do you want us around our decimal points?
4 decimals.
Or do you want us to round it up?
Generally in this class, probabilities will be 4 decimals. Percentages will be 2 decimals, generally in this class. So whenever you have to report percentage, it'll be probably in 2 decimal places. And then probabilities will be in 4 decimals. So yeah, 4 decimals will work. Now, be careful. You only get 2 attempts per answer box, right? If you want to get 100, like right now, I can't change this answer or that answer. I can change these because this background is kind of like grayish pink. And this grayish pink, I've used up all my attempts on those 2. I have one left for the other one. So you got to be really careful if you don't want to redo it to get 100%.
Okay, I have a question.
Yep.
Okay, so I'm getting, I don't know if I'm getting the right decimal point, but on the part where it says the probability is getting a number less than less than 3,
How about this? You share.
10.
Can you share? Go ahead and share. You can click on the share screen button in Zoom.
Yeah, let me see. Share screen.
That way, instead of talking about not seeing what we're talking about, it'll be easier for
Okay.
learning purposes to share your screen.
It says host disabled.
Oh, really?
Screen
right.
sharing.
I thought I clicked check. Okay, now you can do it.
Mm-hmm. Okay. Hold on. Here.
Okay, here we go.
Yeah.
Oh,
And my number was supposed to be less than 3.
okay.
I don't know
So
if I'm put.
what,
I don't know.
do you have a Mac or a PC?
I have a PC.
Okay. That's weird. All right. So less than 3?
Yes, I can show
Okay. 3,
the thing.
this 3 over here, right? In cell A4. Click on cell A4.
Mm-hmm.
Click on that. Go ahead and click on it. Okay, that 3 is equal to 3. So you want to delete that
Okay.
0.3 there.
Okay. So it'd be 2 out of 10 instead of 3?
Oh, what you want to do there is just type equals,
Uh-huh.
type equals, and then click on the 0.1. Right, and then pull that up and down.
This up and down?
No, just hit enter.
Oh, this one.
Yeah, that's the probability you want. Now you pull that up. Right? And then
Okay.
delete the one that's in row 4.
Okay, this one.
Yeah, you want to delete that one because 3, you just go ahead and delete it. Yeah. Yeah. And then you got to fix the ones in column C.
This
That
one.
0.5, that should be equal 0.1. So equal, and then click on 0.1. Type
This
equals.
one right here?
Yeah, equals. Delete that, and then just type equal, and then click on the 0.1 right next to it. No, no.
Oh, the point one next to it.
Yeah, just click on it right. No, oh no, no, no. The original
Oh,
data.
the other one. My bad.
Yeah, that's all right. Hit enter. And then what you can do is you can highlight rows 2 and 3.
Drag
Okay,
that down.
That's fine. Yeah, that's fine. And then delete the 3, the 5, the 7. Yeah, there you go. Delete that. Delete that.
Correct.
Now in cell C1, type P. Type P and then even. Or sorry, P parenthesis even. Then close parentheses. Okay, and then D1, you can type what? P.
Yeah, P.
Type P in parentheses, and then capital X less than 3, right? Close parentheses, right? So those are your answers for probability of even and the probability of less than 3.
Okay.
Because 3 is equal to 3, right? So you don't include that in the set.
Okay.
Only 1 and 2
Thank
are
you.
less, right?
Mm-hmm.
Okay, good. All right, sweet. Okay, I think I'm sharing the wrong thing. Stop share. All right. So what I was demonstrating to her was here you could write even, right? And then you can type equal. Notice what I'm doing here. I'm doing equal, and then I'm referring to the original cell, right? You see that? I'm not recalculating anything, right? And then because we want every even number, right? I want the probability of 2, the probability of 4, the probability of 6, the probability of 8, probability of 10, et cetera, right? And then this would be the probability X less than 6. It doesn't say less than or equal to 6, right? So on this one, I want to type equal in that very first one. 1 is less than 6, right? So I want its probability over here. I want 2s, 3, 4, 5, not 6, right? And then the other one is probability greater than 4, probability of greater than 4. Right? Now 5 is greater than 4, right? 4 is not greater than 4, but 5 is. So I'm gonna do this. Right? I'm gonna sum these up, right? Everybody see that? And I'll make them 4 decimal places. I like having probabilities as 4 decimal places because it makes it easier once we get into reading probability tables. generally in the probability tables, the probabilities are 4 decimals. And my last one is probability of x equal to 7 or 4, right? Now I'm gonna go down here to the row that contains the number 4, right? X equal 4. I'm gonna type equals the original probability. And then down here where x equals 7. X is equal to 7 in row 8, right? There's x, and x equals 7 is in this row 8. I'm gonna type equal, and then I'm gonna go back to the probability table, right? I'm just gonna sum those two. That's probably a really kind of an interesting way to model that, right? In Excel. Okay. Any questions on that? Everybody got it? Everybody got that? Can we move on? Anybody still working on question 1?
I need just a couple more seconds. Hold on.
Okay. How do you say your name? Naisha?
It's
What about the bottom parts? As in
Naisha.
NAC?
Oh, we haven't got there yet. We haven't got there yet.
Okay, okay.
How do you say it? Naisha?
Nayaja.
Neaja?
Mm-hmm.
Aja. Okay, all right. I'm
Yeah.
from Idaho. We're very bad at pronouncing stuff. Like city in Idaho will be spelled
That's
Du
fine.
Bois, right? We call it Du Bois, but the French would pronounce it Dubois. And then Coeur d'Alene, I'm not sure how you pronounce that French, but like cul-de-sac, that's not how the French. That's a town in Idaho, cul-de-sac. It means the corner of the sack. Yeah. So we're not very good with pronunciation. We're horrible, actually. And then everybody mispronounces. It seems like most people mispronounce my name initially. They all think it's Hall. My first name is Hall and my last name is Snare. I've heard that about 1,000 times. But I just remind people, it's like Pal Star. Pal Star. I'm a pal and I'm a star. I'm a pal who happens to be a star. All right, Naisha, are you good? Everybody else good? We're gonna work on question 2 now, right? I'm gonna blow it up so you can see it better. I'm gonna put the numbers down here. Now, first, what do you have to do with this problem, number 2? How do you find the number in A? How do you find the number in A? How many things are in A? In my Venn diagram,
You have 4 numbers.
exactly. You have the intersection of A and B, which is this kind of light blue or dark blue section of a football, right? And then you have this, I don't know what this is called, but this is purple. Yeah, this is the
We'll just call it
intersection.
Navy.
Huh?
Why don't we just call it Navy for simplicity?
Okay. This is navy. Well, we got purple, right? Purple is the intersection
Yeah.
of A and C. Blue is the navy blue is the intersection of A and B. And this darkest color, this like triangle looking thing, it's the intersection of A, B, and C, right? This is the intersection of A, B, and C. Okay, so you have 3 intersection quantities or counts in A, and then you have the things that, the 12 things in A that are mutually exclusive with B and C, right? So we got to add, so the number of things in A, let me do this. Call that just A. and then I'll do A, then I'll do N for and, A and B, A and C, and I'll do A and B and C, right? I'll do the thing for B, just B, B and A, B and C, and then B and A and C. Oh, don't need that one because I already have it right here, right? I'm over counting. If these two are the same thing, right? I'll move this to the bottom. Move that to the bottom. We want to overcount it, right? And then I need just C. Then I need C and A, which is overcounting too, right? We're overcounting. A and B. Don't need this one. Let's do this. I got A and B, A and C. Delete. All right, now I'm just kind of messing things up. So I'll do it this way. There we go. We got 1, 2, 3, 4, 5, 6, 7 regions, right? 1, 2, 3, 4, 5, 6, 7. And then we have not A, B, C, right? I got 21. Oh, that's O, outside. O means outside here. I can't, yeah. O means outside of A, B, and C, right? Outside. And I have 21. So for my just A, I have 12. My just B, I have 10. My just C, I have 18, right? 12 are in just A, 12 are in just B, and 18 are in just C, right? And the intersection of A and B, I have 9 right there, right? A and C is the intersection of A and C right here. 7. And the intersection of B and C. Oh, I got a mistake. I got a mistake here. Let's do this. I just noticed this. Just A and B. Just A and C. Just. Because A and C includes the 4 and the 8. Or, sorry. The C and B includes the 4 and the 8, right? A and C includes the 7 and the 4. And A and B includes the 9 and the 4, right? So this right here is the intersection. This football on the tee, kicking tee, this football here is the intersection of A and B. This football on its side, kind of on its side, that's the intersection of A and C. And this football here is the intersection of A and B, right? So that's why I had to correct it, right? That's why I had to correct it. Well, I don't know if that's a correct way to do that. I think it's all right. This just A and C does not include stuff outside of that, right? This is a very strict count. Right? Just B and C, 8. And then A and B and C is 4. Okay. So the number in A, I'm going to write little lowercase n, A, here. Okay, then I'm going to use equals and go back to where it's an A, right? Okay, so I got the 12. I got the 9 that's in very restrictive A and C and B. Then I got the intersection, right, of all three. Oops. I can call this N here, by the way. These are the mutually exclusive classes here, right? I think we're trying to create mutually exclusive classes. These are the mutual, we have 8 mutually exclusive classes. Just 8, A, just B, just C, the very restrictive just A and B, the very restrictive just A and C, the very restrictive just B and C, and then the intersection of A and B and C. And then outside of A, B, and A, O is outside of A or B or C, right? So this should be 21 here, right? In my case. So essentially we're just adding the 12, 9, the 4, and the 7, right? The 12, the 9, the 4, and the 7. What did I do that for? Sorry. I thought that was the total. So I need to do the total here. Sum. Right. Sorry. Good thing I didn't hit enter. I can sum this now, right? So my total number of observations in this experiment is 89, right? But I'm gonna drag that over. And I get 32, right? So when I counted them by hand, 12, 9, 4, and 7, I'm like, wait a minute, that's not 21. When I looked at it, 12, 9, 4, and 7 is not 21. That's when I realized that I had copied the 21 over. So it's actually 32, right? 9 and 12 is 21. Then that's 28. And add 4 more is 32, right? Okay. What about A and C? Well, to get A and C, to get the number of A and C, I need to get the ones that are just in the very restrictive A and C, right? And the ones that are in the intersection of A, B, and C. I can't add that phrase. I got to add numbers, right? I got to get this one down here. Yep. Again, if you just look at this football from here over to here and then down around here, you got 7 and 4, right? That's 11. Okay. Now we got a tricky one. What is in A and B, but not in C? A and B right? That superscript C there means complement, right? Means complement. So A and B is the 9 and the 4, right? The 9 and the 4, A and B. But you can't include anything in C, right? So A and B and not C is just this. This right here, A and B and not C. So we have to have the intersection of A and B, and then we got to exclude anything in C, right? So it's just the 9. Oh, I can't copy that. I'm going to use a apostrophe Excel for not C, right?
You should be able to do a subscript just as easily.
Yeah, I know. I mean, I can use that, or I can use a C and then I can make it a subscript, right? It's just you have to point and click more. Font, here we go. Superscript. There we go. All right. So I just drag that over and I get 9, right? So I type in 9 here, right? So I'm using the phrase just A and B, right, for this set here. When I write just A and B, that means A and B and not C, right? Not Z, right? National Socialist, not the letter C, right? So I just want to make sure everybody understands that. That was kind of like a joke, I guess. I guess those are homonyms, two things with different meanings that sound alike, like there and there. Okay. And we've already calculated that one, right? I have these 8 mutually exclusive groups. You add it up and you get 89. Mine, I get 89, right? Now I want to calculate the probability of A, right? Now I want to calculate the probability of A. All I got to do to calculate the probability of A is do this. Right? I get the number in A, and I divide by the number total, right? Yeah. I'm going to reduce it to 4 decimal places. I'm going to paste it right here. So you can think of these as freaks right here. These are freaks, frequencies. And these down here are relative freaks, right? They're relative freaks. All right, now I got to get the probability of A and C, right? I'm going to just go ahead and copy these two. And then change the N to P. I'm going to change that to probability. So that's the probability of A and C. This is going to be the probability of A and C, or probability of A and B, not C, right? Not letter C. Whoa, what happened? I lost my computer screen, or I accidentally hit the power button on my TV. Hang on. Got to move my remote. Okay, so the probability of A and C, well, I have how many things in A and C? I have 11 things in A and C. I have a total of 89 things, right? Reduce the number of decimal places, 4. And then how many things do I have in A and B and not C? I have 9. I have a total of 89 things, right? Again, reduce the number of decimal places to 4. So this is 0.1236. And this is 0.1011. Anybody have any questions on that one? We're all good? So just kind of reviewing these ideas of probability, right? And you think of relative frequencies as probabilities, right? We're all good? Anybody have any questions? Everybody's caught up? Everybody's caught up? We're all good? Moving on. Okay, we have a bag that contains 6 blue marbles, right? So we have blue marbles here, right? I have blue marbles, green marbles, and 5 black marbles. So what I'm going to do, I'm going to write the colors up here, right? Blue, green, and black. And then below the blue, I'm going to do an O for a marble. How many marbles do I have? I got 6 blue marbles, right? 3 marbles, 4 marbles, 5 marbles, and 6 marbles. Right? 6 marbles. And then green marbles, I have 10. I'm going to get rid of one of the black marbles. So I have 5 here, right? And then I need to add 4 marbles here. I'm going to make these blue. I'm going to make these green. Because some people are, more visually, they're more visual learners. And then I'll leave these as black. Right? I'll make them a brighter color green. Okay, so I got blue, green, and black, right? Okay, so how many total marbles do I have?
21 for you. Dealer
Yeah.
has blackjack.
Count. Count A. So I got 6 blue marbles, 10 green marbles, and 5 black marbles, right? That's what I start with, right? Now it says if under replacement means that when you draw a marble out, you check its color, right? And then what do? You put it back in. So this is the probability of drawing a blue marble and then a black marble, right? Okay, so bag contains 6 blue marbles, 10 green marbles, 5 black marbles. If one marble is drawn from the bag and put back in the bag after its color is recorded, so we have replacement, what is the probability of drawing a blue marble and then a black marble? Okay, so there's a total of how many marbles? Total number of marbles. I got some. I have 21 total marbles, right? All right, so we want to know the probability of drawing a blue marble. And then the word is and, right? And. So on the first poll, right? So I would think, and they're all mixed up, right? They're all mixed up, right? They're all mixed up. So this would just be what, 2 divided by 21, right? Divided by 21. And the key word here is and. Right? So imagine you have all these marbles. You have all these marbles in there, right? You have 21 marbles in the bat, and they're all jumbled up, right?
Sir,
I
for
think I
your
did it wrong,
case,
didn't I?
for your
Yeah, I think I
case
did it
with
wrong.
number 3, I
Yeah.
was thinking
Yeah, I got it. I did it wrong. How many blue marbles are there total? There's total 6 blue marbles, right? I got it. Sorry. The total of 6 blue marbles, right? So let's do this. Probability of, sorry, we have probability of blue, right? So this is my first marble. First marble, right? Probability of blue is what? There's 6 in there, right? 6 marbles in there. How many total marbles are there in there? Mine is 21, right? Right? That's the probability of getting blue, right? Okay, so on the first marble, there's 6 blue in there, and there's 21 total, right? Right. Now, if we get a marble, if we pull a marble out, whether it's blue, green, or black, we put it back in, right? Do this. I'm trying to do this in a way. Okay, so total. Blue. And this is gonna be probability. Okay, and I'm gonna replicate this down here. Bear with me for a second. I'm trying to do this in a systematic way. Okay, so there's a total of how many marbles in there? That first pull. Start with 21, right? Start 21. And the number of blue marbles is 6, right? The probability of blue is what? This divided by 21. Now, this might seem straightforward, but hang on one second. Okay, so we're only looking at the first marble picked, right? So there's an order here. Blue is picked first, and then black is picked second, right? So in the first marble, there's a total of 21 marbles in there, and there are 6 blue marbles in there. And that ratio is the probability of blue on that first pick, right? In replacement, right? Under replacement, right? Under replacement, when we pull that first marble out of the bag, what do we do with it? We look at it, we go, it's blue, black, or green, right? And then what do we do with it? We put it back in the bag, right? We put it back in the bag. So when we're doing that second marble, right? When we're in the second marble, what are we doing? When we pull out that second marble, how many marbles are in there? 21, right? Right? The second marble's got to be what? In my case, black. Right? How many marbles are black? 5 in my case, right? Okay. So total 21 we put the marble back and we want the probability of black. Well, that's 5 divided by 21, right? 5 divided by 21. But close to what it was, right? The one was. Now, are we done? Craig, are we done? What do we have to do? What do we want? Why do I have
Essentially,
and capitalized? I have and capitalized because what do we have to do? When we're talking about the word and, we multiply probabilities, right?
yes.
Multiply probabilities.
In your case, it's gonna be 6/21 multiplied by 5/21.
Yeah, or since I'm using Excel, I want blue and then black, right? So the probability of blue, my case is that, right? Word and means multiply probabilities, right? Right? So to get blue and then black, the probability is, for me, is 0.0680. I gotta take a break real quick. Hang on. 0.680. Hang on a second. And then we'll come back to, why don't you guys try the next one on your own, all right? And then we'll see if you get it right.
About another thing. Yeah, I mean, it's hard to put it on. That's what she said. That's what she said too. She's like, you know, it's so white, right? Because a lot of people don't do that.
All right, you guys figure out the next one? Okay, and this one, when you pull the marble out, whether it's blue, black, or green, right, you leave it out, right? You leave it out, right? So under no replacement, whoops, under no replacement, how many marbles do you have in the bag now?
In your case, it's 20.
Exactly, right? I'm gonna make this red and bold, right? Under no replacement, that marble's out of the bag, right? So now I only have 20 in there. Right? What's going on here? Okay, under no replacement, only had 20 marbles left, right? Okay, see that? There's only 20 marbles left. So the probability of black changes, right? It changes now. Right? Yep. Now you can make this. Now let me ask you this question. Why don't we, can black be the first marble picked? It can be, right? In my case, you can pick a black marble, right? You can pick a black marble, but this problem requires what first? It requires blue first and then black, right? If this was black and then black, right? This would be black and that'd be a 5. This would be 20 and this would be black and this would be 4. You see that? But this problem requires blue first. We don't know what the probability of blue first and then black, right? In my case, it's 0.0714, right? See the difference between replacement and no replacement? And this is what what's going on with the Powerball. What's the first 5 numbers in the Powerball? You reach in and you grab a ball, you pull it out, and then you leave it out, right? And on the second pull, you reach in and you grab the second ball out, and then you leave it out. And then you go back in, you grab the third ball, right? So on the first 5 balls of the Powerball drawing, there's no replacement. But with the Powerball, you're picking that from a completely different barrel, right? You're picking that Powerball from a completely different barrel, right? But on the first 5, there's no replacement. If there is a replacement, it changes the probabilities, it changes the payouts, right? All right, the last question here is, in a number guessing game, you ask a person to guess a number from 1, that's weird. I got 1 there twice. So I got rid of this 1 right here. You ask a person to guess a number from 1 to 24. If the person makes a random guess, what is probably their guess will be less than 6? Well, that's pretty easy, right? We've already done this, right? We did this above, right? We did this above. So we can do 1, 2, 3, 4. I'm going to pull this down to 24. My number is 1 to 24, right? So I got 1 to 24 there, right? Again, the probability is 1 divided by 24, right? For all of these. The sum of any probability distribution is 1, right? Sum. Those all add up to 1, right? Whoops. Okay, and we want to know what is the probability of their guess will be less than 6. So 1 is less than 6. I'm just equals. I'm doing the arrow over. 2 is less than 6. 3 is less than 6. 4 is less than 6. And 5 is less than 6. Somebody's going to add those up, right? So I'm going to add up those 5 probabilities, right? There's only 5 of them. In my case, there's 5 of them because I want the probability that the guess will be less than 6, right? What's the probability of x less than 6, right? And each one of these is the probability of x, right? This is x. when we want to calculate the probability of x less than 6, we have to add up these 5 probabilities. Another way to think of that is the probability of x equal 1, or x equal 2, or x equal 3, or x equal 4, or x equal 5, right? Under or you add, right? Under or you add. Okay. So mine is 2083. Right? Any questions on this first half of the lab?
Nope.
Everybody got it?
Yep.
So it's just getting your noodle wet for probabilities. And what do we know about probability distribution? Each probability is between 0 and 1, right? Positive values. It can be 0, it can be between 1, and they can be equal to 1, right? The sum of the probabilities equals 1, right? Sum equals 1. All right. Anybody have any issues with that? Those 4 questions? Those are pretty easy, right? Not too bad. I almost messed up the third one. I was overthinking it. Honestly, I don't teach this class very often. This is the first time I've taught the class in a couple of years, so I get a little rusty. But you get in a situation where you kind of mess up, and then you don't give up. You don't throw your hands in the air and wave them like you just don't care, right? You just go back to the drawing board, right? I didn't have time to review this before we started. I had office hours until 1 at Mercy College, and then got the subway and just got my kids, got them home from school, and then I came up and started doing this. So I haven't had a chance to even look at this yet. I think the last time I looked at it was maybe a couple years ago. I don't know. All right, the next problem, question 2, right? So question 2, this is an application of what we call Bayes' rule. This is Bayes' rule right here, right? This is the probability. D is the event what? D is the event that an employee is a druggie, right? That's D, probability of a druggie. POS is the probability that you test positive on a drug test, right? So POS is test positive. D is the probability that you're druggy, right? C is the probability that you're clean. C is not D, right? D is druggy, not D is clean, right? So this is the complement of D, right? All right, so for safety reasons, your company's distributions. For safety reasons, your company's distributions. I think I gotta fix that. That doesn't make sense. I gotta edit that real quick. Your company's board of directors. I don't know why I have distributions there. That's funny. Okay, that's better. For a safety reason, your company's board of directors do not want employees using drugs. This could be a pilot, right? Have you guys seen the movie Flight with Denzel Washington? Right, he's a very functional drug addict, very functional alcoholic. But generally, you don't want drunk or drugged employees flying airplanes. And on top of that, you have flight attendants. The Amazon Prime show, the flight attendant's an alcoholic, right? She's functional. My mom was a functional alcoholic. But yeah, certain occupations, you do not want people who are alcoholics or drug addicts. You don't want drug addicts can be impaired on the job. Alcoholics can be impaired on the job, right? So you definitely don't want people who are drunk or drugged out flying a plane, right? So there are reasons why companies do drug tests. In the Navy, we had to do a random drug test like every 6 months when I was in the Navy, right? So the companies don't want their employees doing drugs. They don't want them impaired on the job, right? This company hires a company to do drug testing, right? You hire a lab to do drug testing. The lab claims their drug test is 94.67% accurate, but it has a false positive rate of 2.1%. So the false positive rate is 2.1%. And then your employees were hired from a community where it's pretty common knowledge that 1.08% of the people in this community are druggies, and 145 of your employees have popped positive for drug test, right? So you're freaking out because you have 145 employees who have just popped positive for drug use. So what is the first thing you want to do when you have 145 employees testing positive for drug use? What are you going to do with them? Are you going to fire them? Should you fire them? What do you, oh, I got a hand up. Is my hand up?
Well,
Maybe-
to answer your question, I can give you one. If they prove themselves to be irredeemable, I have them blacklisted or something. And I say that because you don't want them to be a menace to you. So, and with that, I don't think you want them to be a menace anywhere else.
Okay. So, but you have these 145 employees, right? What are you going to do with the 145 employees? Are you going to fire them? You can say
Well,
it. You can say it. How many people to fire the 145 employees? If a baseball player tests positive for steroids, what should be done with the player?
he
Suspended,
should be barred.
barred, suspended, right? That's
Yeah.
what most people will think, right? Most people will say, let's just bar them, let's fire them. But now look at this. 1% of the people in the community are druggies, right? That 94.67% accuracy rate looks pretty awesome, right? The thing's 95% accurate. It's only got a 2.1% false positive rate. The 145 employees, man, if they tested positive, they're a druggie. They're inebriated on the job, right? So I think a lot of people would say, yeah, fire them, right? Anybody know what Lee Corso says on Home Depot's ESPN Game Day show? Let me know what he says. He goes, not so fast, my friend. All right, so we're thinking fire these people, right? They tested positive. Let's apply Bayes' rule and find out if that's a good business decision. Okay, so given a randomly chosen employee is a druggie, what is the probability of an employee testing positive for drug use? Where did I get this number from? Where did I get that number from? How does where does that number come from? How do you get that number? If you're trying to figure out how effective your drug test is, how would you find out what that number is?
You just simply take the lab test accuracy and just divide it by 100.
Okay, but yeah, that's how you get this from that, right? Okay, so the
Yeah.
question is now, how did the drug lab get that number that I highlighted? How does the drug lab get that number? They have this test, right? And they claim that this test is 94.67% accurate. How are they getting that number? Well, they can go to a place where they know people are using drugs, right? They go to inner city neighborhood, maybe in Manhattan, and they're you could observe white people, black people, Hispanic people, all the different kinds of people on the street. You see them shooting a drug in their vein on the street, right? Male, female, whatever. Could you use that as a population? Though the people on the street doing that in plain sight, right? You could put them in your trial, right? They're using drugs, right? They're using them because you can see it right there out in the open, right? So a drug company might say, let's give them our drug test and find out what percent will test positive, right? Right? You follow? So if you could find 10,000 people that accurately represent the population of the United States, probably about 60% white, 50% female, 12% black, 13% Hispanic, et cetera, et cetera, et cetera. If you can find a group of people that you are known users, and then you give them this test, then you can come up with this number, right? You all see that? So that's why it says, given a randomly chosen employee is a druggie, right? So you take a bunch of people and you put a bunch of them in one room, they're the druggies, and you put a bunch of people in another room, they're clean, right? You give the druggies the test, and you give the clean people the test, and you have the two ratios, right? So if we have 1,000 people, or we have 10,000 people who are drug users in one room, and we have 2,000, well, sorry, let's do 100. We have 100 people in one room who are drug users, and we have 100 people in another room who are clean, right? We give those 200 people this test. About 95% of the drug users in that drug room are going to test positive. And 2 in 100 of the ones that are clean are going to test positive, right? So in the 100 clean group that are given this test, 2 of them are going to test positive. In the drug user group of 100, 94 or 95 are likely to test positive, right? And that's where they come up with these rates. You can also probably use mice, right? You'd use mice. Mice are pretty homogeneous. Humans are not as homogeneous. So I'm not sure how they do this mice, but that's the intuition behind the accuracy rate and the false positive rate, right? Ideally, you want to give your test to 100 known drug users, and then give your test to 100 known clean people who haven't tested positive for anything or haven't used anything. And you give them the drug test, you test their urine or whatever, you test their blood or their urine, and you get 95% roughly of the drug users testing positive, and you get 2% roughly of the clean people testing positive. There's a Seinfeld episode where Elaine eats a poppy seed muffin and she tests positive for heroin use, I think it was, opioids. And she can't go on a international junket because her boss thinks she's a druggie when all she did is eat a poppy seed muffin. Right? So there's reasons why people test positive falsely, right? All right, now where do the 1.08% of the people in the community are drug use? Right, that number would be like in a small community of 100 people. I grew up in a town of 60. One guy uses drugs, and everybody in that community of the 100 people, they have a pretty good idea who that one person is, right? So all that means is there's not a drug issue in this particular community. In rural communities along the Appalachian Mountains, there's been an explosion of drug use. And there's been also an uptick in drug use post-pandemic amongst people too, right? People were isolated. And now you have a lot of people who are taking illegal drugs that are laced with fentanyl. And that's causing what, 100,000 deaths a year? So I think drug use, the media makes drug use more acceptable behavior than it was in the 50s. People kind of did it under the table in the 50s. Now people in New York walk around with marijuana cigarettes, illegal and legal. They walk around with them and they smoke them in public, right? You wouldn't have saw that 20, 30 years ago. If you did that 20, 30 years ago, you'd have been busted and put in jail, right? I'm not advocating drug use or no drug use. I use caffeine. So caffeine is really addictive, right? And it's a stimulant. People drink beer. Beer is a depressant, right? Beer is a depressant that's legal if you're 21 or older, right? So people use drugs. Sugar, you can think of sugar as a drug. People get addicted to sugar too, right? So sugar, caffeine, and alcohol are legal drugs, right? Okay, so that's where that number comes from, right? This number comes from what? How do we get this number here?
We
This
just
is the prob-
simply subtract the P positive D from 1.
Yeah, exactly. So it's the probability of testing negative given you're druggy, right? And this is the probability of positive given you're druggy, right? This is probably, so these both involve a group of people that are known drug users who either test positive or test negative for drug use. And I would argue that this is a good drug test because this is a high number, close to 100%, and this is a low number, right? Close to 0, right? So I'd say that's a good drug test, right? Down here is you have, this is the what? This is the false positive rate. So this is the probability that you test positive given, the line means given that you're clean, right? So they get this number from testing a bunch of clean people. And only 2.1% of clean people test positive for drug use. This down here is the probability of negative given that you're clean, right? So this is probably that you test negative given that you don't use drugs. And so I would argue with these 4 numbers, it's a pretty good drug test, right? Now this number, where'd this number come from? Where do you hire employees from? You hire your employees from this community where people believe there's no drug use going on, right? Now that could be an accurate subjective probability, or it could be an inaccurate subjective probability. There's really no way to know, right? There are people that can drink a case of beer and be functional. If I have 2 beers, I can black out. So I rarely drink ever, right? In the Navy, I got in trouble a couple times. My buddies could drink like a case of beer each, and I'd have like 4 or 5, and I'd be completely blacked out and not knowing where I was at, right? So I like the taste of beer. I like the taste of a porter, a stout. Occasionally I like a extra special bitter, an ESB, or a pale ale, but I mostly like stouts and oatmeal stouts and porters. But I rarely have anything to drink. I get drunk really easily and I black out. All right. So we're all very unique people, right? But I'd argue that this stuff works. So if you have a bunch of lightweights in your community, like me, right? If this were an alcohol test and you have a lot of lightweight alcohol people like me, then this prevalence rate would be be perceived to be a lot higher, right? But if you have a lot of people in your community who have high, if you have a bunch of heavy drinkers who have high tolerances, this problem seems like it's a lot smaller than it actually is, right? If everybody had a high tolerance, you wouldn't think there was an alcohol problem, so this number would be small. But if everybody was lightweight like me, then this number would be big, right? So these probabilities, these subjective probabilities, are kind of based on like experience, right? They're very subjective, right? There's a lot of assumptions behind them. There's really no way to tell this. I mean, if you're asking people how many drinks do you drink a day, if somebody drinks 5 drinks a day, they're probably going to say 1, right? So there's a bias to minimize how much you drink in a day, right? Or how much drug use, how many drugs that you consume in a day, right? There's kind of like a bias toward clean, right? In the United States. So this is the community prevalence rate, right? 1.08%. And this is just 1 minus that, right? So you're either a druggie or you're clean, right? So it's just 1 minus that. So this is the complement of that. C is the complement of D. Negative given C is the complement of a positive given C. A negative given D is the complement of positive given D. So you kind of need all those numbers there to calculate this probability, right? Now, the thing that you want to know as the employer is this. This is what you want to know as the employer. You want to know the probability of your employee being a druggie given that person tested positive for drugs, right? That's what you're really interested in. You're not interested in this, the probability of positive given the person, the probability of positive given that you gave this test to a bunch of druggies. You're not interested in that, right? You're interested, you want to know this number. What's the probability that the employee that tested positive for drugs is in fact a druggie? That's what you want to know, right? And you have to use Bayes' rule to calculate it, right? So what I'm going to do is I'm going to copy this. I'm going to copy this. Where's my snipping tool? I can't see my snipping tool. All right, I won't copy it. For some reason, I can't see my snipping tool. But that's all right. Okay, so what I want to do is I'm going to write the probability of positive given druggie. Next to it, I'm going to write the probability of druggie. Right? I'm going to put this in 2 cells. I'm going to copy that. I'm going to put it down here. Why did I put it down here? Because this is that, and that is this, right? So the probability of positive given your druggie times the probability of druggie, that's the same as this part here, right? And then I'm going to paste it over here. I'm going to change it. I'm going to change this to clean. I'm going to change this to clean. I'll see that. Yep. And then I can delete this. I'm going to put a line underneath I'm going to put a line underneath there. See that? I'm going to put a plus right here. Yep. But down here, I'm going to copy this. I'm going to copy this here. I'm going to replace this with what it equals. What is the probability of positive, testing positive, given your druggie? Given the people administering the test were druggies. This right here is 0. This right here is 0.001. 0.9467. Oops. What's going on here? Oh, numlock is off. 0.9467. That's that number right there, right? What is probability of druggy? In my model, probability of druggy is 0.0108. Okay. I'm going to copy. Well, I'll just do this. Do equals. I'll come up here. And then I'll do equals. I'll come up here. Okay. All right, now what's the probability of positive given clean? The probability of positive given clean is 0.021, right? This is the false positive rate, right? False positive rate. And what's the probability of clean? The probability of clean is 0.9892. Okay. I'll follow me. So I'm just plugging the values into this equation here. One step at a time. Now what I'm going to do is I'm going to take the product, the two numbers on top. I'm going to multiply them together. What's going on here? Uh-oh, what's going on here? Weird. Try that again. Equal. Oh. Let me reopen. I think I'm having an issue with Excel. Hang on. This happened to me last week. Okay. Equal. I'm going to come up here and get that. I'm going to multiply it by. I'm going to multiply those two together, right? I'm going to put a line under it. Oop. Okay. And then remember, this times that equals this times that, right? So what I'm going to do here is I'm just going to type equal, then go up here. And then this is just plus, right? This is just plus. Then I got to multiply these two together, right? Okay, so this is the product of those two probabilities. This is the product of those two probabilities. And this is the product of those two probabilities, right? So now I got to do what? I just got to get one number, right? Equal that divided by parenthesis this plus that, right? So I'm just taking the number in blue and I'm divided by the sum of red and purple, right? Red and purple. So this divided by this sum down here. And when you do that, you have to do the sum first, which is why it's in parentheses, right? Order operations matter. So what is this number here? This is the probability of what? It's the probability that your employee is a druggie given the person tested positive for drug use. Right? Does that seem very high? Does that seem odd? Wouldn't you think that probability would be closer to 1? Shouldn't that be closer to 1? Right? It should be closer to 1, right? Because if it was equal to 1, then you would say the probability of a druggie given you're positive is 1, right? But it's not. Right? It's not close to 1. It's kind of a long ways from 1, right? It's shocking, right? Because the drug test says it's 95% accurate, right? Roughly 95% accurate. This is like, whoa, that blows my mind, right? The probability an employee is a druggie, given the employee tested positive. So what you're doing here is you're taking all the people who tested positive, right? All the people who tested positive, which is 145, right? 145 people tested positive in your company. Right? 145 people tested positive. Right? So many people tested positive. Of those 145, only 33.98% are actually drug users. Right? Interesting, right? The probability of employee is clean given the employee tested positive for drug use. Well, remember that's just a complement of that, right? So that's just this. So this is the probability of in a druggie given you tested positive. Right? This is the probability you're clean given you tested positive. Can't see near the lights turned off. That's the number of
And
people
how'd
who
you get the 145?
This is that's given up here, right? That's given up here.
Oh,
145. I give it to you, right? So of the 145, right? Of the 145, about 33% tested positive. I mean, were druggies, right? So these are all the people that tested positive in your random drug test. Only 33% are actually using drugs. 67% are clean, right? So most of the people who tested positive are actually clean, right? Oh, wait a minute, what happened here? Oh, I already entered that number. This is the 67. I think I got 2 tries, right? So roughly 33% of my people who tested positive are using drugs. 67% of the people are not using drugs, which is crazy, right? Again, you're interested in this probability here, not the accuracy rate of the test. So all we got to do down here is just multiply. Multiply this number. Where's equals that? This number times the 145, right? And we got to multiply this probability times number that's positive. And then we reduce the number of decimal places to 0, right? So 48 drug using employees fired for failing the drug test. Yeah. 48 drug using employees were fired for failing the drug test. 97 clean employees were fired for failing the drug test. Right? Crazy.
All right, I got a perfect score on both of them.
Nice. Isn't that crazy?
Well,
think
it is quite a large number.
Yeah. So if you're a rural community and most people are churchgoers, they're not using drugs, and there's no incidence of people being drunk or inebriated from alcohol or drugs in the community. There's no arrest, and everybody seems sober, right? You probably don't have a drug problem. The prevalence rate is probably low, right? if the news comes out and says a teacher in that community was selling methamphetamine out of her basement, what might the school district do? It might be outraged and then issue a drug test. And anybody that fails a drug test is fired, right? Well, you're setting
Well, that's
yourself
why-
up for,
Go ahead.
yeah, you're setting yourself up for a lawsuit, right?
Not to mention,
Yeah.
well, that's the problem. Even though you're sober, you're still prone to false positives and false negatives.
Yeah, exactly, right? You're still prone to that because sometimes something you eat might affect the test, right? So, in a community that's relatively clean, right, there aren't any issues. There isn't public intoxication, whether it's from drugs or from alcohol, right? And there's one person that's selling methamphetamine in the community. Maybe they're selling it to somebody in a nearby city, right? They're making it in this city and then selling it in another city, right? If the city panics and if people are outraged, they might drug test everybody in government work and they might drug test everybody at the school. And then you're gonna end up firing a lot more clean employees than drug using employees, right? And then you're setting yourself up for a lawsuit. And you'd use this logic in court to raise this reasonable doubt, right? So explain why the likelihood that the company will be sued for wrongful termination is
High.
high, right? And we just explained why, right?
Yeah.
Well, it's high because only 48 in my case of the people who tested positive are actually drug users. 97 of people who were fired were clean employees, but they had tested positive for drug use, right? So
49 to 101 respectively.
You had 101?
I had 49 and 101 respectively.
So you can see why there's going to be a probably lawsuit coming, right? Because everybody thinks if you test positive for drug use, you must be a druggie. When A-Rod popped positive for steroid use, people are like, yeah, those tests are really accurate. But if I was his lawyer, I would probably use a Bayes rule argument to suggest that he is one of the 97, right? Not one of the 48.
Yeah.
All right.
All
It
right.
looks like you're the last one on, Craig. Everybody else
Yeah.
dropped off.
Yeah.
you have
Well,
any
in
questions?
that case, I'm gonna go ahead and we'll go ahead and say thanks for all this.
Okay, cool.
So
How
I
you
guess
doing
I
in your
can leave
homework?
now?
How you doing in your homework?
Huh?
Are you doing all right with your homework?
For the moment, I'm okay. All right. In that case, I'm going to go ahead and take my leave. That's okay, sir.
Okay, yeah. If you need any help, come to office hours tomorrow and Wednesday.
Yes, sir.
Okay, cool.
Bye.
All right, good night. Bye.